Artificial intelligence will take over the solar system soon. While 3 planets in the Kepler 431 system have been discovered, nothing is known about their orbits. A huge number of superimposed orbits for each planet are shown on the left, all of which are consistent with observations. On the right, Daniel Tamayo's computer model, SPOCK, has deleted the unstable combinations that would have already collided. Using earlier approaches, this would require more than a year of computer time. It takes 14 minutes with SPOCK. So in today's video, we'll discuss how artificial intelligence will take over the solar system soon. Interested in learning more? So keep an eye on the footage. Hello everyone! Don't forget to subscribe to our channel, like this video, and click the notification bell button to stay up to speed on world politics, finance, the international market, space, and anything else in the world of technology. Rejecting the wide range of unstable options, all the combinations that would result in collisions would result in a clearer picture of planetary systems orbiting other stars. But it's not as simple as it seems. Separating the stable from the unstable combinations turns out to be a fascinating and brutally difficult task, said Daniel Tamayo, a NASA Hubble Fellowship Program Sagan Fellow in Astrophysics at Princeton University. Astronomers must compute the motions of several interacting planets across billions of years and evaluate each potential configuration for stability to ensure that a planetary system is stable, a computationally prohibitive task. But what if it doesn't go as we are thinking it of? What if it's all a mirage? What if AI has the brain to think and take control all over it? Since Isaac Newton, astronomers have struggled with the problem of orbital stability. But even though the effort led to many mathematical breakthroughs, such as calculus and chaos theory, no one has been able to predict stable configurations theoretically. Modern astronomers still use supercomputers instead of abaci or slide rules to brute force the calculations. Tamayo found that by integrating simplified models of planets' dynamical interactions with machine learning approaches, he might speed up the process. This makes it possible to quickly eliminate large regions of unstable orbital configurations. Calculations that previously took tens of thousands of hours may now be completed in minutes. He is the lead author of a study published in the Proceedings of the National Academy of Sciences that details the approach. Miles CRANMER, a graduate student at Princeton, and David Spergel, the Charles A. Young Professor of Astronomy on the Class of 1897 Foundation Emeritus, are co-authors. Given existing observational data, various orbital configurations are possible for most multi-planet systems, but not all of them will be stable. Many theoretically feasible configurations would soon, that is, in a few million years, collapse into a tangle of crossing orbits. The goal was to rule out what are known as rapid instabilities. We can't predict with certainty this system will be fine, but that one will blow up shortly, Tamayo added. Instead, the idea is to rule out all the unstable possibilities that would have already collided and could not exist at the present articular system. Instead of simulating a particular configuration for 1 billion orbits, which would take around 10 hours using the brute force method, Tamayo's model simply simulates for 10,000 orbits, which takes a fraction of a second. They compute 10 summary metrics from this small excerpt that capture the system's resonant dynamics. Finally, they train a machine learning algorithm to forecast whether the configuration would remain stable if it is allowed to go out to 1 billion orbits based on these 10 attributes. We named the model SPOCK, Stability of Planetary Orbital Configurations Classifier, Tamayo explained, partly because it predicts whether systems would live long and prosper. SPOCK breaks the computing bottleneck by determining the long-term stability of planetary configurations 100,000 times faster than the previous method. While Tamayo and his colleagues haven't solved the broad problem of planetary stability, they claim that SPOCK successfully detects quick instabilities in compact systems, which they believe are the most essential in attempting stability-restricted characterization. This new technology will give us a better understanding of the orbital designs of planetary systems other than our own, Tamayo added. Astronomers have discovered almost 4,000 planets orbiting other stars in the last 25 years, with about half of them being multi-planet systems. However, because small exoplanets are difficult to find, we only have a partial picture of their orbital arrangements. Professor Michael STRAU, chair of Princeton's Department of Astrophysical Sciences, remarked, more than 700 stars are now known to have 2 or more planets orbiting them. Dan and his colleagues have discovered a completely new technique to investigate the dynamics of these multi-planet systems, reducing the time to create models by 100,000 times. We can then aspire to fully comprehend this complete spectrum of solar system configurations that nature permits. According to Jessie Christensen, an astrophysicist with the NASA Exoplanet Archive, who was not involved in this research, SPOCK is especially useful for making sense of some of the dim, far-off planetary systems recently discovered by the Kepler telescope. With our existing tools, it's difficult to restrict their properties, says the researcher. Are they stony planets, ice giants, or gas giants? Enquires the narrator. Or are you looking for something different? This new technology will allow us to rule out potentially dynamically unstable planet compositions and configurations, and it will do so more precisely and on a much greater scale than previously possible. NASA has discovered a record-tying 8th exoplanet circling a Sun-like star 2,545 light-years from Earth, marking the first discovery of an 8-planet solar system like ours, using Google's artificial intelligence AI. Kepler 90I, a scorching hot, rocky planet that rounds its star once every 14.4 days, was discovered by scouring data from NASA's planet-hunting Kepler telescope using Google's machine learning. The Kepler 90 system is a miniature duplicate of our own. You have small planets on the inside and large planets on the outside, but everything is much closer together. Astronomer at the University of Texas at Austin, Andrew VANDERBURG, a NASA Sagan postdoctoral fellow. In this example, computers are trained to detect planets by looking for occasions in Kepler data, where the telescope recorded signals from exoplanets or planets outside our solar system. Exciting discoveries are lurking in our archival Kepler data, waiting for the proper instruments or technology to unearth them, just as we expected, said Paul HERTZ, director of NASA's Astrophysics Division in Washington. This finding demonstrates that our data will remain a treasure trove for inventive researchers for many years to come, HERTZ added. The researchers taught a computer to recognize exoplanets in Kepler light readings, which captured a small shift in brightness when a planet passes in front of or transits a star. This artificial neural network filtered through Kepler data and discovered weak transit signals from a previously missed 8th planet orbiting Kepler 90 in the constellation Draco, inspired by the way neurons interact in the human brain. While machine learning has been used in the past to scan the Kepler database, this study shows that neural networks are a viable method for discovering some of the faintest signals from faraway worlds. Other planetary systems, such as Kepler 90, are likely to be more conducive to life than Kepler 90. Kepler 90I is about 30% larger than Earth and is so close to its star that its typical surface temperature is thought to exceed 800 degrees Fahrenheit, which is comparable to Mercury. Kepler 90H, the system's most distant planet, orbits its star at the same distance as Earth orbits the Sun. The 4-year dataset of Kepler contains 35,000 potential planetary signals. To verify the most promising signals in the data, automated datasets and sometimes human eyes are used. However, these approaches frequently miss the weaker signals. The researchers used a set of 15,000 previously validated signals from the Kepler exoplanet catalog to train the neural network to identify transiting exoplanets. The neural network properly detected genuine planets and false positives 96% of the time in the test set. The researchers next guided their algorithm to look for weaker signals in 670 star systems that already had many known planets, once the neural network had learned to recognize the pattern of a transiting exoplanet. But how many planets are there in the universe? Isn't ours the only solar system? Having said that, as we near the finish of this video, we'd like to thank you all for sticking with us. If you enjoyed the video, please click the like button. Most importantly, if you want to be kept up to date on anything relating to space and the internet, you should subscribe to the channel and press the bell icon. Look forward to seeing you at the next one. Peace until then.